tell you about that's in Minnesota, and this one provides data on the various elements in the core, and it does this by X-ray fluorescence. This is a technique that geologists have been using for over 100 years, but the old instruments, you'd have to take a sample, you'd have to prepare it and run it, and it took lots of time. What's good about this machine is you put your core in here, and it passes through the machine. It's like a big pizza oven, and it takes high-resolution analyses every 2 millimeters. And so it gets a lot of data, and it doesn't use up the core. And the type of data it gets is about a suite of 30 elements, from aluminum all the way through to uranium. And some of the elements are useful for us, and in particular, if we look at one of the core sections, this is titanium, and this one is calcium. And titanium is a mineral that, or it's an element, excuse me, that is commonly associated with sand and silt and clay-sized grains. These are the typical types of minerals that we find in soils and transported in rivers. So it's giving us one kind of signal, and then the calcium is associated most likely with the mineral calcite, which is present in some of these lighter layers here. And this is very different because the mountains that surround the Rieti Basin, they're made out of limestone, calcium carbonate, and so when the water enters the system, it dissolves the carbonate, and that travels through the groundwater, and all of the springs in the lake are very rich in this type of water. And what we see is that after the water enters the lake, we can precipitate layers that are rich in this mineral. So these two signals behave very differently from each other, and it's going to be Claire's job to try and figure out precisely what these signals mean. So in the last few minutes of my portion, I just want to show you some of those results. This is a core from Lago Lungo, and these are the zones that Scott talked about. And the 2009 core was about 5.5 meters long. So it pretty much stopped, I guess it stops right here. And all of these red lines are lines that match up to the older cores. So this would be the Renaissance zone here. This would be the modern industrial zone. And then here we're into the medieval period, and then the Black Plague is about right here. So this is a period where, based on the pollen and the other proxies, we have the Little Ice Age. It's a cooler climate. We have reforestation, and we see some interesting patterns. Now, I found that the best way to look at this data from the beginning is to just kind of squint your eyes and look at the big pattern. And overall, there's a lot of structure up at the top. Some of this we think has to do with dissolution of minerals, and that's bad because that's going to erase the original signature. But probably the parts that interest me the most are a little bit further down, because this is older than the previous cores. And if you look, you kind of squint, you can see there's a change that occurs right about here, or maybe even a little bit lower. And we see this change in the magnetic susceptibility, which is this curve here. We see it in some of the elements. This is titanium, manganese, and calcium. And if we look at the actual core and the sediments, we also see the change. So this is an enlargement of a small portion, maybe right here, of this interval. We call this banded. You can see the white layers that are calcium carbonate. There's a whole variety, and this is the most variable part of the core. From a climate standpoint, the interpretation is that this is a drier period. This is the time where perhaps there was active deforestation, open grasslands. And what's interesting contrast this part with lower down, where it changes, and I don't know if you can see it as well, but it's not as variable. The sediment is dark. It has some olive and black coloration to it. And if you look at the chemistry, there's an interesting trend in the calcium where it's higher calcium here, and then it decreases. Then there's some periodic spikes in here. So it's going to be interesting to try and interpret what exactly this calcium signature means. Why are we depositing more calcite here? And there's many reasons for that. It might be differences in the inflow. Do we have groundwater? Do we have flooding and runoff that would dilute the calcium? Are the temperatures higher? And that would also allow more calcium to deposit. So this is something we're going to continue to work on.